Hello there. We are now beginning Chapter 10, which involves conics, parametric equations, and polar coordinates. We don't cover all of this chapter. In fact, we only cover the first 4 sections of this chapter. But before we begin, I want to apologize for my nasally voice as I am enjoying a cold right now. This is section 10.1, which involves conics and calculus. Basically, there's a lot of just basic information regarding conic sections in this particular section. So really, you should have already learned a lot of the material that's covered in this section. So it should be a little bit of a breath of fresh air for you as we go through this. There are a lot of slides in this particular section, but it's a lot of definitions and formulas and that sort of thing. As I go through them, I'm going to quickly go through all of the definitions and all that stuff because one, it's something that you've already learned in the past, and two, it's something that you can easily take the time to look up and read on your own. So I don't want to make this an extensively long video going through the things that you've already learned. So instead, what I'll spend a majority of the video on is going through different examples that you will see in your homework. So I hope that will suffice. Basically, as you've probably learned in one of your algebra classes or a trig or a pre-calculus class, is that there are 4 conic sections. There's a circle, parabola, ellipse, and a hyperbola. And each of those is created by intersecting a plane with a cone. And you can see those illustrations below. Here, we don't really do a lot with this, but it's called a degenerate conic, which I think is kind of funny, but I guess that's the immature side of me. But you can go ahead and take a look at this. Now, this slide here basically tells us that there is a general second degree equation that can be used for every one of the 4 different conics. And so they all can be written in this manner, basically standard form of a conic, but it's not ideal to have them written in this way because there are other ways in which we can write the equations of different conics that helps us identify which type of conic it is, and it allows us to see the different properties that can be used. Now, the first conic involves a circle, and you should recognize that this is the standard equation of a circle. It's actually nice because H and K represent the center of the circle. So the center is HK, and the radius is R. So if you're given a formula like this, it's easy to graph the circle and then identify important parts of the circle. We're not going to spend a lot of time graphing circles and looking at equations of circles in this particular class. We will, however, spend a bit of time on parabolas. Remember, the definition of a parabola is the set of all points that are equidistant from a line and a fixed point. The line is called the directrix. The fixed point is called the focus. And I want to remind you that the vertex splits these equally. So the distance from the vertex to the focus is equivalent to the distance from the vertex to the directrix. The directrix, if you're ever asked to find the directrix, that is always an equation. It's an equation of the form x equals or y equals, depending on if the parabola is opening up or down or right or left. So this is kind of the gist of the parabola. Now, theorem 10.1 gives us the standard equations of the parabola. So a couple things to recognize here. The vertex, just like the center of a circle, the vertex is HK. Be cautious of the signs because in the formula we have minus signs. And then, as mentioned before, the directrix, depending on the direction in which the parabola opens, the equation for the directrix are here of the form x equals or y equals. If the parabola has a vertical axis, that means the parabola will be opening either up or down. And the way you can tell by the equation is whether or not the x value is squared or if the y value is squared. If the y value is squared, we'll have a horizontal axis and the parabola will be opening left or right. So again, a couple things here. Notice that we have a 4p here. The focus is p units from the vertex, so that's why that is helpful. And then down here, this tells us the ordered pair of the focus, which is just the point. Okay, so this is basically the information that you'll need when dealing with parabolas. Okay, so let's just jump right into some examples here. Example 1 says find the vertex, focus, and directrix of the parabola and then sketch its graph. Honestly, when it comes to sketching graphs of these, I'm not going to be super concerned about that because it's just, I mean, there are so many technologies available to graph these things for you. Okay, so you may notice that this equation here is in that standard form that all conic sections can be written in. So what I want to do is I want to rewrite this so that it's in the standard equation of a parabola. Okay, so what I'm going to do to rewrite this is I'm going to complete the square. Okay, now chances are you do not remember how to do this, so let me help you remember. Now, what we want to do first is we want to make sure that we have x's on one side, y's on the other. So I'm going to leave these here, and I'm going to move these over. And when I do, I end up with x squared minus 2x is equal to a positive 4y plus 7. Now I left some space here because I'm going to come up with a special little number that I'm going to add here. And remember, whatever I do to one side of an equation, I need to do to the other. So I need to come up with a special little number. And the way I come up with that number is by taking b divided by 2 squared. And b in this case is the coefficient of the x. So that's going to be negative 2 divided by 2 squared, which is negative 1 squared, which is 1. 1 is my special number that I will put here and here. Okay. Once I have done this, now what I want to do is I want to factor this side and then simplify this side. Now, if I factor this, if I have completed the square correctly, I'll end up with a quantity times itself. So this is going to end up being x minus 1 quantity squared. And really, this number comes from my special little number before it's squared. So this is always what will end up here. Food for thought. Now on the right hand side, I'm just going to combine like terms and end up with 4y plus 8. Okay, now I'm getting really close to the standard form of my equation. The only thing I need to change is I need this side to look a little different. So I'm going to factor out a GCF. So the left-hand side remains the same. This is my GCF. And I want to remind you that this here is supposed to be 4p from our formula. Well, I have the 4. That means that p must be 1 from the standard equation of a parabola on the previous slide. Okay, so this is exactly the way I want it. From here, I can identify h is positive 1 and k is negative. Sorry, you probably noticed this should be a 2. My bad. Sorry about that. So that is a negative 2. Okay, be cautious of the signs. All right, so now I pretty much have everything that I need to find the items that have been requested of us. The first thing we are asked to find is the vertex of this parabola. Remember, the vertex is where the line changes direction. So the vertex again is HK. We already have determined that H is 1, K is negative 2. We also need to find the focus. I want you to remember that the focus is the ordered pair that is p units from the vertex. So recall the focus in this case is going to be h plus p comma k because this parabola opens up. Or I'm sorry, to the left. No, this one opens up. I apologize. I'm sorry. So this will become h is 1, p is 1. So this is going to be, I am deeply sorry. Once again, I was looking at the wrong thing. The focus in this case, I am sorry, is h k plus p because this opens up. This is the vertex. This here is going to be the focus. So we are moving up p units from the vertex. So 1 comma k is negative 2, p is 1. So when we add those together, we get a negative 1. So this is the focus. Lastly, we need to find the directrix. When we find the directrix, that is going to be the line. In this case, it'll be a horizontal line, p units from the vertex. So this is going to take the form y equals k minus p because it's always below the vertex. So in this case, we will have y equals a negative 3 for our directrix. The last thing we are asked to do is sketch a little picture of this. Again, I'm not super concerned about the picture or the sketch. The vertex is at 1, negative 2. The focus is at 1, negative 1. And the directrix is here. So your parabola, just a little sketch of this, should look like that. And that wraps up the first example. The second example is the same type of thing. Okay, this example is the same type of thing, but you may notice that the y is squared now. So this parabola will be opening right or left instead of the previous example. So you might want to pause this and see if you can complete the square on this given equation. Now, in order to complete the square, we're going to keep the x's and y's together. So the y's will stay put and the x's will move over. So we'll have y squared plus 6y is equal to a negative 8x minus 25. Don't forget, we will be adding our special little number. So let's try to find that special number. Remember, that special number is b divided by 2 squared. B in this case is 6. 6 divided by 2 is 3, and 3 squared is 9. So the special number that we will be using is 9. Okay, so moving on, I need to factor this left-hand side. When I factor this, I end up with y plus 3 quantity squared is equal to, over here when I combine like terms, I get a negative 8x minus 16. I need to take a GCF out of the right-hand side, and I'm going to take out a negative 8. So I'm left with x plus 2, and I did that right this time. Good job. All right, remember, this here needs to take the form 4p. So my final equation will be y plus 3, that quantity squared, is equal to 4 times negative 2, because 4 times negative 2 is equivalent to negative 8 times the quantity x plus 2. From here, I can identify, now be careful with your h and your k. H always goes with x, which is over here. So this tells me that h is negative 2. This is k is negative 3, and p is negative 2. Okay, so I have everything I need. First, the vertex, again, is hk. So my vertex in this case is negative 2, negative 3. The focus here, now the thing to pay attention to, and it might be helpful to think of what the graph looks like at first. This graph, we know it's going to be opening left or right because the y value is squared. If p is negative, which it is, then our graph will be opening to the left. If p is negative when the graph is going up and down, that negative will mean the graph's opening downward. Okay, so you want to identify whether or not p is positive or negative. Okay, so since our graph is opening to the left, the focus is going to be to the left of the vertex. So our vertex is going to be h plus p, comma, k. So when we do that, we will end up with a negative 4, negative 3. The directrix here, our directrix will be to the right of the vertex. So it's a vertical line, so it's going to be x equals h minus p. So in this case, we will have x is equal to 0. So when we sketch this, let's see. Our vertex is at negative 2, negative 3. Our focus is to the left of that. Our directrix is to the right of that. So it's going to look like this. Okay, and again, it's just a sketch and not something I'm super concerned about. Here's another type of problem that you will see involving parabolas. It will say find the standard form of the equation of the parabola with these given characteristics. Okay, so we're given the focus and the directrix, and there's actually some pretty important information that we should be able to identify from this given information. The directrix is x equals negative 2. So if I sketch that, x equals negative 2 is here. And we know that that's on the outside of our parabola. Since this is a vertical line, this tells us that our graph is going to open either left or right because the vertex will be vertical then. So that means that we need to figure out which of the formulas to use. The formula that has the parabola opening right or left has a horizontal axis, which means my formula needs to, or my standard form of the equation needs to take this form. Okay, so we also know that the focus is at 2, 2. Okay, so our focus is here. Well, this tells us that the distance P from here to here, that's the same thing, that is a distance of 2. Okay, we can also identify from this that the vertex has to be in the middle of these. So our vertex then is 0, 2. So this is H, this is K, and we know P. We can plug it into our formula. So we will have y minus k, which is 2, quantity squared, is equal to 4 times p, which is 2, times x minus h, which is 0. And if you want to simplify the right-hand side, you can, but this is what I would be looking for. Not so bad, right? Okay, so let's move on. So here on this page, basically it's just kind of giving you a little bit of information regarding basically some real-life applications of parabolas. Go ahead, take some time, look through this. Same type of thing on the next slide. Here it just kind of gives you some information about how lights can be reflected in a parabolic shape. So I'm not going to take the time in the video to talk about this. There's also a reflective property of a parabola. It's interesting how many real life applications there are of parabolas. And if you look through the book, there are some different examples, but I'm not going to take the time in this video to go through those. Instead, we're going to move on to the next conic, which is ellipses or ellipses. An ellipse, as defined here, is the set of all points whose sum is the distances from two distinct fixed points called the foci. Some people call it foci, foci. I don't really care. I don't suppose I really know. Tomato, tomato, as far as I'm concerned. The line through the foci intersect the ellipse at 2 points called the vertices. So these here would be the vertices. Okay, so you have something in this case. This line here would be called the major axis. And then the vertical line would be called the minor axis in this particular case. And I say this particular case because this has a horizontal major axis. Sometimes there can be a vertical major axis as well. So here, this slide kind of talks about it a little bit. A chord joining the vertices, again, is called the major axis, which its midpoint is the center, also referred to as HK. The foci are on that major axis, and then there's the minor axis as well. When we are writing our equation, there is a value called A in our equation, And A is the distance from the center to the vertex. So that's on the major axis. On the minor axis, the distance from the center to the other side of the ellipse, that is a distance of B. Then sometimes the distance C is helpful. The distance C is the distance from the center to the focus. Okay, and we'll take a look on the next page. So here is the standard equation of an ellipse, and here there are two of them. And again, just like a parabola, there are two because it depends on if there's a horizontal or horizontal or vertical major axis. A horizontal major axis, the parabola is sideways. A vertical major axis, it's vertical. In the equation of an ellipse, we always have a plus in between the two fractions, and we always have the equation equal to 1. Now, some things to pay attention to here. Again, the center is HK. The major and minor axes are 2A and 2B. If we have a horizontal major axis, the foci are found by taking H plus or minus C, comma K. It is a K. And the vertices are found by taking H plus or minus A, comma K. And then on the other hand, if we have a major vertical axis, the foci are found by taking H, comma, K plus or minus C, and the vertices will be H, comma, K plus or minus A. One other thing to pay attention to is you will have a horizontal major axis if A. Now, okay, one thing to notice is A is always bigger than B. So if the bigger number is under X, you have a horizontal major axis. On the other hand, if the larger number is under Y, you have a vertical major axis. And that's the best way to tell which one it is. Here's the equation to find the foci. So the thing to notice here is that to find the foci, we have a minus sign. So be careful of these signs because these equations look very similar to a hyperbola, but the signs are opposite. Okay. One last type of thing to know about ellipses is the eccentricity. The eccentricity helps us determine how oval the ellipse is, because an ellipse can still be a circle if A and B are equivalent. So depending on how oval it may be, can be found by the eccentricity. So E is equal to C divided by A. Okay. Let's see, there's a little bit more, it looks like. I already kind of talked about this. You can pause the video and read through this. Here, this talks about some real-life applications of ellipses and the orbit of the moon. You can read through that. And then this gives yet some more information. Okay, let's jump into some examples. All right, so this problem is very similar to what we saw for parabolas. In this case here, it says find the center, foci, vertices, and eccentricity of the ellipse, and then sketch the graph. Okay, so just like before, what I want to do is I want to complete the square. But this one is going to be a little different because from our standard form of our equation, we want both variables on the same side. So what I'm going to do is I'm going to group together x's, leave it on the left-hand side, and I'm going to group together y's, leave it on the left-hand side, but then I'm going to move this constant over. So what I end up with is going to be x squared minus 6x. I'm going to leave a little space here for my special little number. And then for the y's, I'm going to have plus 10y squared plus 20y. And then I'm going to have a different special little number is equal to negative 18 plus those two special numbers, because whatever I do to one side, I need to do to the other. Okay, and now what I'm going to do is I'm just going to complete the square on these two pieces separately. Okay, so completing the square over here, when I do that, I'm going to take a negative 6 divided by 2 squared. This gives me a negative 3 squared, which is 9. So my special number here is 9, and 9 over here as well. Okay. So when I continue with this little piece here will be x minus 3 quantity squared. Same type of thing here. Now the thing to be careful of is we have a coefficient in front of the squared term. So what I need to do is I need to take that out. I need to factor that out and rewrite this. So 10 times y squared plus 2y plus 1. Well, sorry, we don't know our special number yet. Sorry. Okay, so find our special number. In this case, we'll take 2 divided by 2 squared, which is 1 squared, giving me 1. So my special number is 1. Now, the thing you need to be careful of is, since my special number is 1, I'm really multiplying that by 10. So my special number over here is going to be 10 times 1, which is 10. Okay, so be cautious of that. Now, when I rewrite this, I need to keep the 10 out here and then factor this. When I factor this, I get y plus 1, that quantity squared. All right, so now when I am simplifying this, I end up with the quantity x minus 3 squared plus 10 times the quantity y plus 1 squared is equal to, simplifying all this, I get 1, which is outstanding. Now the only thing that looks a little strange here is that these are not not fractions, and I want them to be fractions. So what I'll do is I will divide this by 1, and this I'm going to divide by 10. Okay, so in this case now we should be able to tell what A and B are. Okay, I'm sorry. This should really be 1/10 right here. And the reason for that is I don't want a coefficient out here, but this still needs to be 10 times this. And I don't want to multiply everything by 10 or divide everything by 10. So really, B is going to be 1/10. So from here, I can identify a lot of things. Now, this is a squared. So if a squared is 1, then that means a is 1. Here, this is really b squared according to the formula. So that means b is the square root of this, which is 1 over the square root of 10. I also know from this formula what h and k is. H, and again, I know a is bigger than 1/10, right? So the bigger number is under the x, which means I'm going to have a horizontal vertical axis. Okay. A we have found, so h is 3 and k is -1. Okay, so let's go ahead and find all of the things that we have been asked for. First, the center. We know the center is HK, which in this case is 3, -1. We have been asked to find the foci. The foci, remember, is 3 plus or minus C -1. So we still need to find C. That's one thing we haven't done. To find C, according to the formula, C squared is A squared plus B squared. I'm sorry, minus A squared minus B squared. So when we do this, just for the sake of time, you guys, you should get C equals 3 over the square root of 10. Okay. So that's what I'll add here. So my foci are, 3 plus or minus 3 over the square root of 10, comma, -1. The vertices will be 3 plus or minus A, comma, -1. And 3 plus or minus 1, comma, -1. Or that's what it is after I plug in A. Sorry about that. If you want to write this as actual ordered pairs, fine. That will be 4, comma, -1 and 2, comma, -1. So sketching a quick little picture of this. Let's see. Our center is 3, -1. Our vertices are 4, -1 and 2, -1. So we can just sketch this like so. Okay, not so bad. We might see something like this for an ellipse as well. Here we're given some characteristics and we want to write an equation. So it tells us the center of our ellipse. The center of our ellipse is 1, 2, which is here. And it also tells us that our major axis is vertical. That's really helpful because if we know our major axis is vertical, we can jump right away to the standard form where the larger number is under the y. Okay, so now we will know a little bit more. So we know the center, and then it tells us that these points are on the ellipse. So it says 1, 6 and 3, 2, which is here. Well, if these points are in line with the vertex, that tells us the distance of A, since this is the vertical axis, and it also tells us the distance of B. So from this given information, we know A is 4 and B is 2. We know the center. We have everything we need to write this equation. So our equation is x minus h, which is 1, that quantity is squared, over 2 squared, which is 4, plus y minus 2, that quantity squared, over 4 squared, which is 16, and this is equal to 1. So that is the equation of our ellipse. We now move on to hyperbolas, and here the definition, once again, of a hyperbola is the set of all points for which the absolute value of the difference between the two distances is called the foci. That distance is constant. The line through the two foci intersects at the vertices. So here, if I have my hyperbola, the center again is HK. The vertex is A units from the center, and then this here is the focus, and that's C units from the center. So this is called the transverse axis. You can have a horizontal or a vertical transverse axis. So the line segment connecting the two vertices, as previously mentioned, is the transverse axis, and then it separates the midpoint of that is the center. The distinguishing feature of a hyperbola is that it has two separate branches, and those branches can either open right and left, or they will open up and down. They look kind of like parabolas, but they are not parabolas. Just like the other conic sections, we will have two equations depending on if we have a horizontal transverse axis, which looks like this, or a vertical transverse axis that looks like this. Some things to recognize in this case: these two fractions are separated by a minus sign, whereas when we find the foci, C is separated by a plus in this equation here. In a hyperbola, A squared does not need to be bigger than B squared. You will notice that A squared is always first, and it depends on the variable above it. If X is first, so the positive value is X, we will have a horizontal transverse axis, whereas if Y is first, then we will have a vertical transverse axis. Those are the things to recognize here. One thing that is different about hyperbolas is that they have asymptotes, and the asymptotes kind of determine what those branches look like. So the asymptotes are these guys here. They go through the vertex, and they kind of help identify the shape of those branches. When you graph these, what I always tell my students to do is first find the center, find the vertices, and then find these other points, which is a distance of B from the vertex, and you make this little square. When you make the square, you connect the corners for the asymptotes. Okay, and this information here kind of helps you with that. Okay, let's move on. Here, this helps you find the equations of the asymptotes. They're just equations of the lines, so it's not horribly difficult to find the equations, but here's all the information to do that. Here it just kind of shows you the asymptotes again and how to make a quick sketch of it. Again, you guys, I am not concerned with whether or not you can sketch these very well, because that is not a topic of this course. So let's jump in to an example. Here I've given you the equation, and now from this equation I want you to find the center, foci, vertices, and eccentricity, and then sketch a little graph. So from here we need to make a couple observations. The first observation is that we have y written first. Since y is written first, that means I have a vertical transverse axis, which means my my hyperbola will be opening up and down. From this equation, I can easily identify the center of this. Remember, just like the others, the center is HK. Just be cautious where H is. H is always next to the X. So H is a positive 5 and K is a negative 3. So we have found the center. We can easily find the vertices from here. The vertices, recall, since this is going to be opening up and down, the vertices are these here. So from the center, we're going to move up and down A units. It's always A. So from our center, which is this, we're going to move up and down A to get our vertices. Well, if A squared is 225, then A is 15 because the square root of that is 15. Similarly, B will be 8 since B squared is 64. So from here, we are going to add and subtract 15 in order to find my two vertices. So my two vertices are 5, negative 18, and 5, 12. Okay. We can find our foci, but in order to find our foci, we need to find C. Remember, C squared is equal to A squared plus B squared in this case. So C squared is equal to 225 plus 64, which is 289. To get C, I need to take the square root of that. So we find that C is 17. So my foci are in the middle here. So from our vertex, which is 5, negative 3, we're going to add and subtract C. So it's very similar to the vertices. So this gives me 5, 14, and 5, negative 20 for my foci. Okay. So we found the foci and the vertices. Now we need to find the eccentricity. Remember, to find the eccentricity, that is C divided by A. We know C is 17 and A is 15, so the eccentricity is 17 over 15. And again, that tells us just how, that tells us basically the distance that we're dealing with. Oh, it wants us to use the asymptotes. So for the asymptotes, since this is a vertical transverse axis, looking at the two formulas, we need to use y equals k plus or minus a over b times x minus h. Again, this is just an equation of a line. There are two of them indicated by that plus or minus because one of those asymptotes will have a positive slope, the other will have a negative slope. So we will have y equals k is negative 3 plus or minus 15 over 8 times x minus 5. Then again, you guys, just a brief sketch. You can go ahead and do this, but it's going to end up looking something like this. Okay. All right. Similar to the other ones, we're given some different characteristics of a hyperbola, and we want to write an equation. I always think it's helpful to use this information and sketch it out a little bit first. So I know my center is 0, 0. And then I also know the vertex is 6, 0. Okay, well that's one of them. All right, and then it goes on to tell me that the focus is 6, 7, 8, 9, 10. The focus is 10, 0. Okay, well, if this is the center, then I should know that this is a distance of A to my vertex. And then this is a distance of C. So from here, I know A is 6, C is 10, so that can give me some helpful information. Additionally, this information tells me that I have a horizontal transverse axis. Since I have a horizontal transverse axis, I should know that my equation will take this form. So I'm going to plug in what I know. Now the problem is I don't know B from this information, but I can find B by using the equation of my foci. Okay, I know there's a plus here. C is 10, so I have 100 is equal to 36 plus B squared. Solving this, I find that B is 8. All right, I have what I need for my equation. X minus 0 quantity squared all over 36 minus y minus 0 quantity squared over 64 is equal to 1. You can go ahead and get rid of those zeros if you'd like. It's up to you. Okay, this wraps up section 10.1. Woo!